Okay. We're going to do this part of the experiment at this point, really. We have already mixed the phenylethylamine with the tartaric acid. The tartaric acid that we mixed the phenylethylamine was pure, but our phenylethylamine was a mixture of R and S. So we have a mixture. Because pair of enantiomers, they have very similar physical properties. So they have same boiling point, same melting point, same solubility, and the acidity. So we cannot use any of the techniques we have learned for separation so far. If they had different solubility, we could have used recrystallization. If they have different boiling point, we could have used distillation. If they had different acidity, one was more acidic than the other, or one was neutral, one acidic, we could use the extraction. If they had different polarity, we could use chromatography. So all the techniques that we learned so far, we cannot use for this experiment to separate the phenylethylamine. The only difference is between the two enantiomer is that when you face them with a chiral compound, a pure chiral compound. So that's why we picked the tartaric acid, and the tartaric acid is pure R tartaric acid. It's going to react differently. It's like you have your right hand and you have your left hand. Usually when I have the students here, I can do better like demonstration with them. If I bring my right hand, it's going to give like a better handshake with someone else's right hand, okay? But if I bring, just a minute, Charlie? Charlie, bring your right hand to me for handshake. Okay, you see the right hand handshake with right hand with the right hand, how fixed and how strong is the handshake? Now, if I try to handshake with someone's left hand, bring the left hand, you see, we're not even sure how we're going to bring this hand, try to make a good handshake, but it still is not a good firm handshake. Like next time, if I was like forced or I had the choice to handshake with someone who's going to right hand is already engaged with something else and the left hand is only available, I might think second time, like what should I do? How I'm going to do this? So this bond is not very strong. So this is the same situation. Let's say tartaric acid is coming with the negative of the amine that we are going to form. The bond is going to form the bond. It's going to be a strong bond, so the crystals are going to be more stable. But with the positive side, enantiomer of that amine is going to form bond. But that bond, thank you so much. For the other side, for the positive one, is not going to be a strong bond. And when it's not a strong bond, then is not going to form the crystal. So we get two different shape of crystals. We get the needle-like crystals and we get the prismatic crystals. So the prismatic crystals, those are the right hand with right hand crystals that we actually need them for this experiment. The prismatic crystals actually stays in the liquid form. So because your hands are chiral, that was the better explanation, like how chiral can react differently with different pair of enantiomers. Right hand with right hand or right hand with the left hand. Very similar analogy that I could. If the reagent is not chiral, let's say if I was going to take this piece of rubber hose, okay, I can hold with the right hand, okay, I can hold with the left hand. The bonding is not different, so it's going to be the same. It's going to be the same if I'm holding with the right hand or if I'm holding with the left hand. Both of them strong, both of them good, and the same surface contact area for both right hand and for the left hand. Why? Because this has a plane of symmetry, is not chiral compound. Because it's not chiral, is going to be the product is going to be the same. The bonding is going to be the same. So the only difference is that when you bring the pair of enantiomer with a chiral compound, and your chiral compound, it has to be pure because we want to get only one pair of diastereomers. So basically what it does, this compound is going to, the tartaric acid is going to form two diastereomers. So we have two diastereomers, and we are going to get two types of crystals, needle-like crystals and then prismatic crystals. Needle-like crystals dissolved in the solution, because we did dissolve them in the solution. Prismatic crystals, they are in the solution now. When we separate them and we add sodium hydroxide, because we don't want to get the diastereomers, we want to go back and we just want to get the pure enantiomer of the S enantiomer, or the negative one. So what we do, after adding sodium hydroxide, we are going to separate the bond between the amine and the tartaric acid, because we want only the amine, and then we can extract that with the we can extract that. We just get the final product, a pure sample. So the technique is called resolution. I didn't cover that in lecture because that's kind of elective for the lecture, but we cover that in the lab, and every lab does this type of experiment with the enantiomers and doing resolution. So what is resolution? Resolution is you change the enantiomers first to diastereomers. When you change the diastereomers, they have different physical property. They have different boiling point. Diastereomers have different melting point, different boiling point, different refractive index, and physical property is different. Enantiomers, they have same physical properties, so they're hard to separate them by physical means. When we change them to diastereomers, then we can separate them by physical means. Then we are going to break the bond between the agent and our enantiomer, pure enantiomer, because we have now only one of them, and we recover the compound of our interest based on the design of the experiment. When we separate this, I'm going to have to test it with the polarimeter. When we test with the polarimeter, we are going to, at that point, phase truth and see how much, how efficient was separation with the resolution technique that I used. And that is going to be determined based on rotation, observed rotation, specific rotation of the final product that I have. If the specific rotation of the product that I have, it does 100% match with the specific rotation of the pure S enantiomer, which is the value is given in here. The value was 40.3. Is given here in page 88. 40.3. That's the specific rotation. If I find the observed rotation, then I calculate the specific rotation. When I have the specific rotation, then I compare that with the specific rotation of the pure sample. So I divide the specific rotation of the observed to the specific rotation of theoretical value. The theoretical value is 40.3, as I said, times 100, and then I get the optical purity, or excess of enantiomer. And from the excess of enantiomer, I can calculate what is the percentage of R and what is the percentage of S. And at that point, we can see how efficient was our separation technique. The machine that we have that is designed, we're actually not sure if you're using the new one or the old one. Okay, at least the one that we were using is going to be, if there is no chiral center, okay? If there is no chiral center in the, if your molecule is not chiral, when we turn this on, but it's missing some attachments, which I'm going to get it. And when we turn this on, there is a filter on this end and a filter, movable filter on the my view, or where I have the magnifying glass and the eyepiece. The light is going to come from this end. It will pass through the sample holder. If I place my sample in this sample in the tube, and I play in the cell, sample cell, I close the cap here. Then I look through the eyepiece using magnifying glass. If the magnifying, when I'm looking at this, like when is that exactly at 0, 0, okay? When it's exactly at 0, 0, I look through the eyepiece. If my compound is not chiral, if it's achiral, I'm going to see something like this shape here, which you have two same shade of the gray color on both half circle. I see the same shade. If the compound is chiral, is going to rotate the light to left side or to the right side, and I would see the rotation of the light, one side dark, one side light. If one side is dark, one side is light, now what I need to do in order to see this again, I'm going to have to move this handle. I'm going to have to move this handle. That I'm doing, I'm rotating the filter. Remember when I used the example for the lecture, when I said that when the light doesn't pass through, if it stops here, I have to rotate the filter in order for the light to pass through. So, and how much has been rotated is the same thing here. I'm going to have to start from 0, 0. There's number here, the movable piece, and then this fixed plate, number 0, aligned with the 0 with no rotation. And then I'm going to move to the left side or to the right side, depends on which side was darker. I'm going to move it until I see the same shade again. When I see the same shade again, then I count by how many degrees the filter was rotated in order to see the light again, and that is going to be my observed rotation. So it would have been better experience if you could have seen through the eyepiece yourself and looking through the magnifying glass. But when I'm using it, I'm going to try to keep as close as possible to the camera, and hopefully you can make more sense out of this. But there's a moving piece here, and there is a fixed plate. And how much are we going to move? We are going to move until the two half circle, they are same shade again. So we are going to move with the procedure at this point. We start in step 8. Step 8, we start the procedure. I'm going to sample. We go get the sample for you, and also I ask for a different polarimeter. And then we set up the vacuum filtration, and I want you to run the chat using the chat. Write down the steps that I need to follow. So when I come back, I'm going to look at your procedure. You tell me what is my next step. I already told you that I stopped step 8 of the procedure, or step 7 of the procedure, you are going to tell. Okay, so do vacuum filtration.
There's 2 buckets of pieces there.
Okay, that's missing pieces. I don't know. Okay, we have the crystals from the other day. The crystals are formed, and I'm going to collect it following your procedure. I need to collect the crystals with vacuum filtration. To connect to vacuum. Change the angle so you could see. Use the filter paper. I'm not measuring the mass of the product, so I don't have to measure the mass of filter paper. Okay. So I'm going to turn on the vacuum and filter the crystal. And you want me to wash the crystals with, methanol? Okay, get methanol. So instead of pouring the methanol over the crystals, I would add it to the flask. This way, if there is leftover of the crystals in the flask, it will be transferred. At the same time, my crystals would be washed. Okay. So rinse the crystals with methanol, and what's next? Place it in the round bottom flask. In a 100 ml round flask. Okay. Please do not to hold the round bottom flask on the table. So I can transfer this. And you're writing the next simple distillation. Okay. So we are practicing extraction. We are practicing distillation. We are practicing all the techniques today. Okay. Going to add 50 milliliters of the sodium hydroxide. Yes. Going to bring 75 and add enough when the two layers is going to form. Going to add 50 milliliters first. See if the two layers forming. It should dissolve and it should form a second layer. If the second layer doesn't form, then I have to add more of the sodium hydroxide. But first, I'm going to try adding a sodium hydroxide and looking for the second layer. Okay. Do you see an oily ring on top? Yes? Okay. So we have the second layer, and as soon as we have the second layer, I can go ahead and set up distillation. You have to set up the simple distillation. Simple distillation apparatus. Hardware first, glassware second. So you want to make sure, I want to make sure my heating mantle is actually working before I set up everything. I want to make sure that this is working. Because if it doesn't work and I find out middle of the experiment, I lose the time. I have to deassemble it. So to make sure it's working first. Okay, it's warming up, so it's working. To support the heating mantle using idling. The utility to support the boiling flask. Distillation head, but to make sure to grease the glass trays. Going to try to use this to support, to make sure I have a sealed system. What is the next piece that I need for distillation? To set up my distillation. What's the next piece? Can you tell me what's my next piece? The glass piece that is missing? The setup for simple distillation. What is missing? A condenser. Just going to add the thermometer, and now I have my condenser. Going to make sure the glass joint is greased. Grease the glass joint and connect. When I'm connecting glass pieces, two pieces of glass, I have to use the cap clamp to hold it together, and I have to use a three-finger clamp to hold the condenser, to support the condenser. Okay. And for collecting, to make sure that I'm not losing any of the vapor or the liquid, it's best to use a vacuum adapter. This one, it's going to make a little bit longer, a vapor doesn't escape and is more directed into receiving container. What should I receive it in? In a flask, beaker, graduate cylinder, or another? Does it say or not? Go to page 23. Okay. And we want to collect 35, about 35 milliliters. You see that it doesn't fit underneath. I have to lift the whole thing up. Usually when you have two people in the lab, it's easier. Each person is going to hold one piece of the glass or one clamp and bring it up. But when I'm working by myself, I should be able to manage this by making everything, all the clamps loose, hold on to the pieces of glass and lift it up at the same time. And then go back and make it tight. So now it can fit underneath. Is there anything missing from the setup? Is there anything missing from the setup? Did I add the boiling chips or no? I didn't tell you, right? If I didn't tell you, that means I have not added yet. So I'm going to have to add the boiling chips. About 2 pieces of chips is good, boiling chips. Now, turn on the heat and wait until it's boiling. And we want to receive about 30 to 35 milliliters of the distillate. Okay, need to connect the water hose, connect the heat, turn on the heat. What should be the setting on the power regulator? The power regulator adjusts the heating rate, the rate of the heating. Should I put it at slow or should I put it at higher number? What does it determine? What should be the setting on the power regulator? What number should I put? Is there a fixed number? It could be a fixed number or it could be just a general answer. So tell me what should I set up? What are the factors? What use for the setting? What do you think? While I'm connecting the water. Any response? No response? Should I set it high? Lower heat allow better, okay, better distillation and no decomposition. And if it's too low, it's going to take a long time. It's not going to form a vapor or enough vapor to reach the condenser. The general rule is you want to have gentle boiling. You don't want too much vapor to be produced, because if too much vapor is produced, then a condenser is not going to have time to condense the vapor into liquid. So we are going to lose vapor. We are going to receive vapor. Actually, the vapor is going to escape, and that means we are losing our product. If it's the other problem was the problem of bumping, we talked about second experiment. Bump, that means the liquid would go in without changing the changing to vapor. So if it's too low, it's not going to boil. We need vapor because it's distillation. We have to change to vapor, condense the vapor to go back to the liquid. So if you don't provide heat, it's not going to vaporize, and we do need the vapor. So we have to look for gentle boiling. At the beginning, you could set it at high to make sure it's boiling. As soon as it starts boiling, you can adjust the power regulator to lower number to provide gentle boiling. And it has to be continuous boiling. We cannot put it too low, because if it stops boiling, then we don't have vapor to condense. We have to generate the vapor and condense the vapor. Okay, what is the next step? Because this is going to take time. You're not going to get the 35 milliliters just like last experiment. It would take time. It's not going to be sudden distillation. I did set it at 80 at this point, but I'm waiting for the boiling. When it starts boiling, then I'm going to lower it for gentle boiling. So at this point, I just set it at 80, between 80 and 90. But when it starts boiling, then I lower the setting. What's the next step after distillation? So I should get ready for it. What should I do? Transfer to the separator funnel. Okay, so I'm going to have to go ahead and prepare my setup for the separator funnel. Okay. Equipment that I don't need, I can put away, so it's not in my way. And I set up a separator for next step. Separator funnel to make sure the height is adjusted, so it's like just below the level of the receiving flask. The gas stopper must be very good. So I'm going to just prepare this. This is just preparation. So while we are waiting for distillate to get to the 35, we don't have a drop yet. So we are waiting for 35 milliliters of that, about 30 to 35 milliliters. But I like to get ready for the next step, and I want to repeat that enough time that hopefully you get the idea. You cannot wait until you get the 35 and then think about, okay, what's my next step? What should I do? So you go ahead and prepare your chemicals, your equipment for the next step. Almost boiling, not yet. The polarimeter that we have it out here, I'm not sure if it's working or not. I'm just going to have to work on that to make sure that is working. And then you watch the distillation for me for now. I'll be right back, okay? Be right back. So if you see like too fast of boiling, send me a message. we just started receiving the drafts, and we found it's working. We're ready for extraction and the polarimeter. We just wait for the distillate to get into the okay. Any questions you have? So add the spatula of sodium chloride in order to make sure that the two layers can be distinguished. Drain the lower aqueous layer, we don't need it. And then from the top, we get the amine. Very good. Good procedure. Okay. Do you have any questions? Questions? I'm gonna look for we have one student absent today, looks like. To bring my attendance sheet and check who is absent. Okay. Jermaine is absent. Any questions for me? No? Okay. Just going to check my email to see if the student who's absent has sent me email or not. Steve, 10 milliliters. It's getting cloudy. You see the receiving. And can you tell me why it's cloudy? What you are receiving in the graduate cylinder now is cloudy. Can you tell me why it's cloudy? Same question for last experiment, right? When you were removing eugenol. But that was a pre-lab question as well. So you knew the answer. Couldn't be the same thing here? Yes? When you are mixing two immiscible substances, so basically it's the part oil droplets in the water. Yes. It's because of the amine is oily, and when it's mixed with the water, it's kind of, you have the droplets of the oil suspended there. Just trying to help you with some techniques and what could happen, or why later on we need the salt to actually separate the oily part, oily layer from the aqueous layer. Salt kind of draws out the water. So if you have a salty water, salty aqueous solution is going to get as much water possible from the organic layer, and then the organic layer becomes more clear or more distinct, so you could see the separation better. Going to get ready for some methanol. Do we have any washing steps for separation? Just drying. Okay, just the separation. So I don't have to get my washing solutions ready. It's coming. Super cloudy. Hopefully we can separate it without. Can you tell me what type of distillations we are doing now? Is this actually simple distillation or fractional distillation, steam distillation, vacuum distillation? What type of distillation is taking place here? A simple distillation. The setup is a simple distillation. But what is actually done here is not simple distillation. What is actually done here is steam distillation, because the steam of the aqueous solution that we have for sodium hydroxide, it provides the water, and the water is going to vaporize, and as it's vaporizing, it's taking the drops of oil, droplets, and bringing up into the condenser. So that's why we are getting like cloudy solution here. I had in the previous edition of the lab manual, when I was writing this experiment, I distillation, and then students, they were looking for the 3-neck flask because that's what we use for steam distillation last class. So I had to change it to just a simple distillation, but the idea is steam distillation. Basically, you are doing steam distillation with the setup of the simple distillation. So steam is bringing the amine into the receiving flask. I increased the power regulator to 100 and the boiling still is not very fast, but I don't want it fast. At least it's gentle boiling. And the boiling chips, let me show you the boiling chips. You see kind of it's floating and it's so it doesn't, it prevents from bumping. Did you take any shots today or not yet? I haven't told you, right? So one screenshot would be from the it asked for a reload. I guess the connection was weak, so I had to reload it. I hope you can see now. So take a screenshot of the distillation setup. Okay, perfect. Okay, about 5 more milliliters, and we should be fine. Because we already have 30 already, so just wait for 5 more milliliters of the distillate. So one of the diastereomers here is soluble in methanol, and the other one was insoluble in methanol. So we could actually wash it with methanol. When we add the sodium hydroxide, the tartaric acid actually dissolves in water. So tartaric acid will stay in the aqueous solution, or if it comes up, it's going to be in the aqueous solution. And the oily part would be the amine. So should I stop the distillation at this point? I think we have enough. I can stop the distillation. Turn off the heating power regulator. Lower and drop the heating mantle. We are going to add. We're going to add the remaining of the recovered solution or distillate into the separator funnel. The two layers have formed to make sure and make it easier for drying the sample for next step. I'm going to add some sodium chloride, but if you look at closely, the two layers have been separated, and now actually you can take your second screenshot for the setup, and that's for the distillation. You can take your screenshot. I don't want to add too much of the sodium chloride because the layers have formed. Also, if I put too much, it gets saturated, it's not going to dissolve, and then it would be hard to remove the bottom layer. So you see the two layers? The top layer is clear. Can you see it? Yes? Do you see the second layer, the oily layer on top? Sort of. Okay. What about now? Can't get any chemicals on my laptop. Can you see it better? Okay. Good. Now I'm going to separate the bottom layer, try to get it out. I transfer the top layer. I transfer the top layer into a beaker. Going to transfer from the top to a dry beaker. You want to make sure the beaker is dry. It's not clear, it's cloudy. That means it's not dry completely. So we have to add the anhydrous agent. Anhydrous agent added to this for this experiment is the potassium carbonate. So we're going to add the anhydrous agent. How much should I add until I get clear solution? When the potassium carbonate stops clumping, solution, the oily solution is clear. When it's clear, it means that all the water has been absorbed. Either my calcium chloride has been open, is not absorbing, or I have too much water mixed, because it took like 3 or 4 spoon spatula. It wasn't a full spatula, but it took a lot of the. Okay, looks like it's enough because the calcium chloride is not clumping. I'm just going to wait until the water is absorbed. Then I'm going to transfer into a beaker that is pre-weighed because we need the mass of the substance for our calculation. So 0. Record the mass of the beaker, 26.664. 26.664. I'm sorry, 28. Sorry. 28.664. Yes. 28.664. Now I'm going to transfer the liquid portion only into the beaker. Okay. $31.7. I'm sorry, 31.47. So this is the mass of the beaker plus sample. You can find the mass of the product. Next step, we're going to add ethanol. Bring some ethanol. Ethanol. Going to measure. The procedure is 7.4, right? 7.4 milliliters of ethanol. Okay. Going to add 7.4 milliliters of methanol. Because that's based on the procedure. And now I have my solution to test with polarimeter. I hope my polarimeter actually is going to, because we are using new cells, hopefully it's going to be enough. If not, I have to add more methanol, and I will let you know if I add more methanol. Just plug in my computer. Turn off in the middle of the experiment. There is no way for you guys to be able to see this. I wish there was a way that you could see it, but there's really no way. It's very tiny eyepiece here. Even I cannot see anything yet. This one fits into. Perfect. It's working now. At least you have to trust me. This is the cell that I'm using to place my sample in. Going to have to add more methanol to fill it up because the cell, when I wrote the procedure, it was based on this cell, 7.4. This one has this bubble here. It takes more, so I'm going to change this to 10 milliliter. So I'm adding 2.5 more of the methanol. Please change that 7.4 in the procedure part to 10 milliliters for your record. Okay, going to put it back because I want to make sure the solution is mixed well. I'm adding just 2.5 more milliliters, 2.6 more milliliters because I had 7.4. Now is 10 milliliters. So the volume of the solvent is 10 milliliter instead of 7.4. So our calculation is going to slightly change. Close it. There should be no air bubbles. So sometimes I have to go back and forth, make sure there's no air bubbles in there. Okay. Okay. When I place the cell inside the sample holder tube, the light is going to be rotated based on purity of the sample I have in this solution, and I can record the observed rotation. I try to take a picture, or I try to bring the camera and for you to see how much has been rotated by how many degrees to record the observed rotation. There's no guarantee that you will see it because it's a very tiny, very, very tiny eyepiece here. Okay. Look for one thing. So we start with this. Okay, we start with this, and we have to change it until we get to this view. So we have to switch it until we get to this view. Going to repeat it a couple times. It's a new machine, so it's slightly different from the machine that I used before, but it's very nice actually. It's much more clear. Okay. Going to take it back to 0, 0. Perfect. Very nice, you know. We can. I'm happy with the machine. So I have to rotate until I get the cutoff. The number for me is 16. 15.9. Okay, 15.9. Record that number, please. 15.9. And this is known as observed rotation. It's very hard to manage for you to see it, but you probably have to trust me based on the number. Can you see anything? Do you see any of the numbers? No? Okay. It's not easy. So not easy because the eyepiece is like it's say to like about 1 millimeter diameter. I wouldn't be surprised if you don't see it. Okay. What is 10? Oh, the milliliter volume would be 10 milliliter. So it's 10 milliliter. And the observed rotation. Okay, perfect. Any questions for me? No questions? Okay. We're done with the experiment. I'm going to stop the recording, but I'm here still to answer your questions. Let me know if you have any questions. And I'm also checking the attendance again.